Here we are, folks. We are making predictions, drawing lines of best fit, part 2. Here's what we got to do. Last lesson, we talked about how to actually draw in the line of best fit. Remember, we said that line would help us describe the pattern, the correlation with what we've got on our grid, on the graph, that is. How do the two ideas, the two data sets relate to each other? Okay, are they showing a positive correlation, a negative correlation? And we said ultimately with that line, we could do more than just show that. We could also take it a step further and say, hey, we can also make predictions. And that line, to a certain extent, was wonderful. For example, we could take this data that I found. We looked at a particular beagle and we kept track of how much it weighed over time and just marked all that down. And notice as the beagle gets older, from 5 weeks old to 10 weeks old and so on, obviously that is increasing. We're showing positive correlation. And in this case, it appears somewhat linear. So by making that line, we can make predictions. Remember, we can use interpolation. So for example, I don't have any data at 20 weeks of age, so I could use that line to help me make that prediction within the data set. I could also use that to predict future weeks. So for example, what happens at week 35, week 45, and so on. We can see what happens there. But today we're going to change it a little bit. Instead of just drawing in the line, we're also going to make the equation, right? And what we can do with the equation is that instead of constantly having to look at this visual and looking at our line, we can write the equation and then just use it. And we can simply plug numbers in that we're looking for and get outputs and use that to make our predictions instead of constantly having to draw new graphs in. So let's get started. First, we need to draw in our line of best fit. So let's do that. Remember, we said the first step to draw our line was to make an oval. Now notice this data does seem pretty linear, so I'm going to do the best I can here. Let's see if we can draw that oval, something like that. There we go. And remember, when we draw our line, so we need a nice straight edge here. We don't want to draw it up here, along this edge. All of our data falls too low. We certainly don't want to draw it down here. All our data would then be up way too high. We want to try to cut this in half, so I'm just trying to eyeball it here. I don't know, maybe something like this. Yeah, let's try it. And remember, do this in pencil. That way, if you make mistakes, you can go back and change it. All right, let's see here. That looks good. Yeah, that looks all right. We got a couple data points above, a couple data points on, maybe one below. That looks fine. All right, let's erase this. We don't need it anymore. And remember, draw a nice big line all the way through the grid. Don't be shy. We want a nice line. And we'll put an arrow at the end here showing that we seem to be trending upward. So now that we've got that, we've got to find the equation of this particular line. So let's go over the process for doing that. First, just like we've done before, when we're finding slope, finding intercepts, whatever, we need to pick 2 points and we need to keep them. Now let's talk about the 2 points. The 2 points do not have to be data points. Take a look. All the data that I've put up here, I've put in a table for you. So there are inputs, the age, and output, the weight. You do not have to pick points. All right, notice in this particular case, my line only hits one of the data points. It really doesn't hit any of the others. So one of the things you need to know is that the points you pick have to be points that are on the line. All right, so for example, this very first data point, 6, 1, is one of the points that does happen to hit on the line. So I'm going to write that down. I know that at, 6 weeks of age, it looks like we're dealing with 1 kilogram worth of weight. So 6, 1. All right. Some other places that you can look for points. If your line happens to cross the y-axis at a nice neat point, that's a good one to pick. If your line happens to cross maybe the x-axis at a nice neat point, that's a good spot to pick. Notice our line doesn't do either of those, so we can't pick that. It gets awful close to this very last data point. So we might try to play with that a little bit. Let's see. It doesn't fall on any nice, neat intersections. If it did, we would definitely select that. So here's what I'm going to do. Since it's not hitting another actual data point, nor is it hitting an intersection, I'm going to take the best guess I've got. So take a look. This last data point is at 30 weeks, and where I'm crossing is just in front of it. So I'm going to say that is roughly at 29 weeks. And notice it hits the line exactly at 8 kilograms. So I'm going to use that point there, and I'm going to make it just ever so slightly dark. Again, not an actual data point, but we're going to use that as our 2 points to help us make the equation of the line. So Making equations of lines. Let's review. First thing we need is slope. Now please understand, when we find slope, we need 2 points. These are the only 2 we've got. We have to keep these points. We are not allowed now to use any other points because these are the points that are actually on the line. For example, I can't use this data point. It's not on the line. I can't use that data point. It's not on the line. This far, far, far green point that I've got over here, also not on the line. We're going to have to use those. So once we pick them, we got to keep them. All right, so we need to find slope first. Second thing we need is to find our y-intercept. And then third and final, write the equation. All right, so let's do that. So our 2 data points, I'm going to do it down here, are 6, 1. Right, that was one of our data points. The other point we said was roughly at 29 weeks and 8 kilograms. Right, so we're going to use that. So step 1, we need to find slope. So m equals, let's see, we'll make this 0.1 and 0.2. So 8 subtract 1 over 29 subtract 6. That's going to give me 7 over, what's that going to be, 23. Cool. So in other words, for every 7 kilograms, it's going to take roughly 23 weeks to do that. Right? And again, we could divide that out, but for our purposes, a decimal is really not going to help here. I'm just going to leave it at 7 over 23. If we want to change it later, we can. All right, step 2, we need the y-intercept. So let's do that. Now let's change color, make it a little easier to see here. So y equals, so that's step 1, y equals mx plus b. We'll number that real quick. Step 1, here we go, step 2. So let's find that y-intercept. So I'm going to use my slope. So instead of m, I'm going to write 7 over 23. I need to pick a coordinate. Again, the only 2 I can use are these. So I can either pick 6, 1 or 29 and 8. I'm going to go with 6, 1. Those are easier points. X coordinate goes in the x position, so 6. 1 goes in the y position, so right there, plus b. Cool. All right, well, let's crunch some numbers. So I'm going to take 7 times 6 divided by 23. Oh my goodness, that's a decimal I do not want to use. So I'm going to change it out real quick for a fraction. Roughly, let's see, we got 1 equals 1 and 19, what is that, 20/3, right, plus b. All right, well, to get rid of that 1 and 19 20/3, we'll subtract that from both sides. So 1 subtract our answer, and obviously we get 19 20/3, oh, 20/3, not 30/3, 20/3 as our y-intercept. Cool. So it's going to cross the y-axis at 0, negative 19 23. All right. Let's put it all together. So that brings us to our third and final step. We need to write our equation. So step 3. Here we go. So y equals negative, or excuse me, not negative, 7 over 23x subtract 19 over 23. Looks good. So there's our equation. So we can now use that equation. Remember, x represents the beagle's age, y represents the beagle's weight. We can now use this equation to make predictions. Let me write it over here. Y equals 7 over 23x minus 19 over 23. Let me show you what I mean. Before we hit those predictions, I want to try something. Take a look. At roughly 10 weeks of age, if we use our line to make a prediction, at 10 weeks of age, we should be looking at the weight of the beagle being just a little bit over 2 kilograms. Let's test our equation out to see if it works. So what I'm going to do, since 10 is the x variable, I'm going to plug 10 in. So let's do that. 7 divided by 23 times 10, so that takes care of that. Subtract 19 over 23. Our answer should be something just a little over 2. Let's try it. Notice that, 2.2 and change. So yeah, it works. Our line seems to be following this equation. We can make some predictions now. So let's see, let's do some interpolation. So in this case, how much should that 20-week-old beagle weigh? Well, based on our line, it looks like it should be just over 5 pounds. But let's use our equation to show that that does seem to match up. So we'll take our 23, now we'll just retype it. 23, or excuse me, 7 rather over 23, multiplied by 20. remember that's our x, that's our input, subtract 19 over 23, and let's see what it gives us. Sure enough, a 20-week-year-old beagle should weigh roughly, we'll round it to the tens position, so roughly 5.3 kilograms. And if we look at our line, at 20 weeks, we're just a touch over 5 at 5.3. So that seems to be a decent prediction. Notice if that, oh, make sure you can see it. Notice if I place that point there at roughly 5.3, it seems to follow the rest of the data. So to take a guess and say a 20-week-old beagle should weigh about 5.3 kilograms seems to be a reasonable prediction, right? If we said that that 20-week-old beagle would weigh 10 kilograms, something's off. All right, let's try another one. Let's try some extrapolation this time, finding data that's really not a part of our set, either too high, too low, that kind of thing. How much should a newborn beagle weigh? So in other words, I'm looking for the coordinate 0, a number. In other words, at 0 weeks of age, what should this beagle weigh? Well, notice my equation already tells me. At 0 weeks, it should weigh a negative 19 over 23. That's weird. This is telling me that not only at 0 will my beagle not weigh anything, it's actually going to weigh a negative amount. Oh, goodness. Well, remember what we talked about last time about mathematical models. Sometimes mathematical models don't always work. And in this case, let's look at our graph again. At this case, we probably can't trust our model, this line, probably much lower than 6 or 7 weeks of age. Because we know that while that beagle will be small, it won't be negative. All right. So again, in this case, I would probably stop all my predictions right at that first data point and go in this direction. Anything back here, probably not going to be accurate. All right. So yeah, while that is our prediction, probably not going to be a good one. All right. Let's see how much a 3-year-old beagle would weigh. So in this case, 3 years. So we'll do 3 times 12. That's 36 months. So we're looking at a 36-month, or excuse me, you're talking about weeks rather. Oh goodness, we got to translate that. I mistaken. Not months, weeks. Helps if you know what you're measuring. So 3 years, goodness gracious, that's going to be times 52. Goodness, we're looking at a beagle that's 156 weeks of age. Mercy, 156 weeks. Wow. All right, let's make that prediction and see what we find. So again, let's use our equation, see what we get. So 7 divided by 23, multiplied our 156-week-old beagle. Let's see, subtract 19 over 23, and let's see what prediction we get. 46.7 kilograms. Now, I don't know about you, but I'm not super accurate about measuring things in kilograms. All right, we measure things in pounds here in the U.S. So 46.7 kilograms. Let's see if we can do a quick conversion here. 46.7 kilograms. Oh goodness, Google won't let me. 46.7 kilograms to pounds. Let's see what it tells me. Oh my goodness, that's crazy. According to our mathematical model, 46.7 kilograms is approximately 103 pounds. That's a big beagle. I know because my brother has had 2 in his lifetime, and none of them were ever that big. So again, what do we remember about mathematical models? Sometimes this breaks down. Beagles, like all animals, will grow when they're younger, but eventually they're going to hit a point where they stop growing, right? And their weight should remain somewhat consistent. This model only thinks it's going to go up. So a 3-year-old beagle weighing 103 pounds would be absolutely terrifying. That dog would be gigantic, and beagles don't get that big. So again, these two numbers that we've come up with, we're going to have to take with a grain of salt. Yes, they are our predictions, but are they reasonable predictions? And in this case, no. A beagle weighing 103 pounds, that's like saying a Chihuahua is going to weigh 103 pounds. It's just not going to happen. We made the prediction, but again, not a good prediction. We're going to have to take the model with a grain of salt. In this case, we could probably do a decent job of predicting things between, maybe 5 weeks to maybe even 30 or 40 weeks of age. But beyond that, the further out we go, the less and less likely our model is going to be accurate. Right? Let's try some more. Take a look. This time I looked at the number of people sitting at a table and the tip percentage. So for example, if you're eating at, say, the Olive Garden, and there's 5 of you at the table, I asked some waiter friends of mine, what kind of percentage tip do you get? Obviously we make tips based on the percentage of the meal. So I had a friend of mine keep some data for me, and here's what he found. That with 5 people, it was just a little bit over 10%, about 12, 13, he said. And I took those data points and graphed them out. So let's see if we could create some sort of equation for my friend to see if we could predict what kind of tip he's going to get based solely on the number of people at the table. One thing I noticed is that we definitely have positive correlation, and it does seem to be somewhat linear. So let's take a pencil, we'll try and draw it in and see what kind of line we can get. So that's the first step. Let's draw our line of best fit. So I'm going to draw my oval in, something like that. That looks okay. Let's grab a straight edge. We'll try and cut this in half. Again, we want to try to have about equal numbers of points above the line, below the line, on the line. And if we don't like what we draw the first time, we can always erase it and try it again. Let's see. That looks okay. A couple above, a couple on, maybe one a little bit above there. That's all right. It may not be the perfect line, but it's close enough. It will work. It will work. There we go. All right, let's erase our oval. We certainly don't need it anymore. All right. We're talking about clusters, gaps, and outliers. I definitely don't see huge gaps, maybe one here. Clusters, maybe a group here, maybe a group here. Outlier, I don't know. Taking that point out really doesn't drastically change things. It might be a touch high, but it's not terrible. So yeah, just to review those terms with you. All right, we need a line. So one of the things we need are a couple of points. I noticed, for example, that this data point seems to pretty much fall on the line, and that seems to be at the point, what is that, 20 people at the table and a 20% tip. So let's go ahead and write that in. So 20 people at the table and a 20% tip, okay? That data point's close, but not quite. So are those. We're not hitting at an intersection. Let's look at our y-intercept. Now notice in this case, our line does hit the y-axis. We might as well use it to our advantage. That's one less thing we'll have to calculate. So let's see here. That's 5, that's 10. That seems to be about halfway. I don't know. Let's call it 7.5. Now that'd be about the halfway point. So 0, 7.5. Those will be the 2 data points that we use to make our line. Let's do it. So first step is to find our slope. So we'll call this point 1, call this point 2. Here we go. So 20 subtract 7.5 over 20 subtract 0. Again, finding points with a 0 in it makes your life a lot easier. So let's see, that'd be 13, 12.5 over 20. And let's see here. We can try and simplify that. Let's multiply it by 100. That'd be 125 over 200. And that would simplify to, let's see, 5 over 8. 5 over 8. So roughly, we're going to get a 5% tip increase for every 8 new people that come to the table. Again, not a great slope, but we don't want decimals in this case. It'll work. All right, let's try and find that. Oh, wait a minute. We've already got the y-intercept. Again, if you can see it on there, it's a lot easier if you go ahead and put it in. So I found the slope. I've got the intercept. Let's write the equation. So in this case, by the way, you might be thinking, Mr. Lamar, what if my line is slightly different from yours? Wouldn't that give me a different equation? And you're 100% correct. However, our slope and our y-intercept should be close enough that we could make similar predictions. Maybe not the same, but similar. And that's how things like the weather, if you look at one news channel versus another, end up being slightly different. Their mathematical models, while based on perhaps the same data, will be done ever so slightly different, and that's what gives us different weather on different stations, depending on who you listen to. So let's try this here. We got y equals, our slope in this case is 5 over 8x plus 7.5. So that's the equation that we can now use to predict what the tip will be based on the number of people sitting at the table. So let's try it. So let's try 17 people. I noticed that 15 and 20 here in between, we don't have any data. So let's see what we can do. So if we're going to predict for 17 people, here's what we'll do. We'll take 5 over 8, multiply it by 17, and then add on that 7.5. So add 7.5. Cool. So we've got something that's just a touch over 18%. roughly 18 and an eighth. So we'll call it 18%. So we could expect a tip of about 18%. And I know if you have big parties, a lot of times restaurants will charge you something like 15, 17, 18% right up front without even asking you. They'll just go ahead and charge it. So yeah, that seems to be moderately accurate. It seems reasonable given the situation. All right, what about 25 people? Notice that would be a real extrapolation situation. We don't have that within our data set, so let's try it. 25, whoop, don't drop it. It works the same way, so 5 over 8 multiplied by 25 people, add 7.5, let's see what we get. About 23%. And yeah, if you've got a great big party like that, typically you'll get tipped a fairly decent amount. So yeah, about 23%. Yeah, that seems reasonable. It doesn't seem too far off the mark. Now, where could this particular model break down? Well, one thing I noticed is that, for example, let's say I was with 4 people, somewhere in here. Well, that's only a 10% tip. And I'll tell you, I have a family of 4, and unless the service was just absolutely terrible, I'm not going to tip them only 10%. It's probably going to be a little bit higher than that. Again, suppose I ate somewhere and it was just 2 of us, maybe my wife and I. Well, according to this model, I would only be tipping the waiter or waitress somewhere, say, 7 or 8%. And goodness, to do that would almost be a slap in the face for most waiters or waitresses today. That just wouldn't work. So again, our model is somewhat flawed. Again, we only have, what do we got here, maybe 6 data points. We would probably need more data from more people to get a more accurate description. But based on the model, I would say, oh, the data we're getting through here seems moderately accurate. Obviously here at the lower end, that seems a little low. So again, we might question our predictions, but for 17 and 25 people, those seem like reasonable numbers. Maybe not the highest that maybe my friend would expect, but they seem high enough. So you get the idea. We're going to draw the line, and instead of constantly going back to the line to make our predictions, we can do it a little bit quicker with the equation. And we know that this is creating a function, and what we've got may or may not be a function with the actual data. But we'll let the function, this mathematical model, drive our predictions to help us figure out what should we predict rather than trying to guess based on the data that we see. We can base it more on the data that we can manipulate through numbers. All right, let's try it one more time. At least we'll try and get it drawn and get the equation together. So take a look. I looked at a swimming pool situation just to see, could we predict how much water is going to be in the pool after a set period of time. So I took some data points. I did this in the fall. Took some data points, and then I'll be honest, I kind of left it to its own devices for a little bit there. Shh, don't tell anybody. And then about an hour in, I started keeping track again. To be honest, I kind of forgot what I was doing there, and went back to taking some more data. So let's see if we can draw a line. So we'll grab a pencil here. Need an oval. Maybe something like that. That seems to work. Not too far off. Let's see. To lob this into, I need to find a ruler because this little piece of paper just isn't going to cut it. Maybe something like this. There we go. Again, do the best you can, folks. Again, if your line isn't exactly where mine is, that's okay. And when we're doing work in class, your line and my line probably won't be in the same spot. That's okay. That's okay. So let's look. I've got a couple of points here above. A lot of my points are below, so that line might be a touch high. But for the sake of argument, we're going to run with it. Let's go ahead and draw this out just a touch more. There we go. That'll work. So 700 hits about here. There's our line. Cool. Looks something like that. Now, one thing I do like about this situation is that my line does seem to hit multiple data points. So that's going to make things easy. And unfortunately, I didn't put the table on here for you, but that's okay. 60 minutes in puts us at about we'll say 270, no, 260. That's what we'll say. 60 minutes in puts us at about 260. So that's how many gallons. And then there was another data point. Where was it? It was somewhere up here. There it is. There it is. That data point there, it was about 10 minutes in, and we were at about 640. There we go. So our 2 data points. Let's make our predictions. Well, first off, of course, we're going to need a line. So here we go. Let's see what we can do. We can do 0.1 and 0.2. So 260 subtract 640 over 60 subtract 10. Cool. So 50 here at the bottom. And if we take our 260 and subtract the, what is that, 640, we'll get a negative number, which notice we would expect that. That is going down. Negative 380. So we'll take that 380 over 50, and we will simplify it. Oop. Well, maybe if my calculator will play ball with me. About 38. Well, yeah, 38 over 5. Well, do we want to do that? It'll work. 38 over 5. Negative. I was going to say a decimal might be better, but that decimal, yeah, that decimal's not a whole lot of fun. It's okay. 7.6. Nah, we'll leave it. 38 over 5 will work. 7.6 gallons per minute is what we're losing, but we'll leave it as a fraction in case we wanted to graph something later. Cool. So there's that. Notice we don't have a y-intercept, so we are going to need to calculate that. And I'm going to go over here because I've run out of space. So there's my slope. So y equals mx plus b. Our slope in this case, negative 38 over 5. The point that I want to use, oh goodness, I don't think it really matters. These are both fairly straightforward points. Let's use this one. So 10 for my x, 640 for the y plus b. You could use either point, you'll get the same answer, folks. So we'll take negative 38, divide it by 5, multiply that answer by 10, and we get, let's see, 640 equals, is that a negative 76? Yep, negative 76 plus b. And we'll go ahead and add 640 in our, what was it, 76? Yeah, 76, making sure I'm reading it right. 716 is b. Cool. So let's write the equation. Y equals negative 38 over 5 x plus 716. Notice that's how many gallons were in the pool when we started, right? That's our intercept, our starting point. So 716 gallons to start. We're draining it roughly, we said, between 7 and 8 gallons a minute. Notice it varies a little bit as we go here, and then heading down. Looks like at around minute 100, thereabouts, it would appear that all the water stopped. Oh goodness, what in the world? TV per day? That doesn't even make sense. What happened there? Oh goodness. Oh goodness, my files must have gotten corrupted. Oh well, we'll make it up. So let's try something here. What if we put in for 40 hours, or minutes rather, goodness, 40 minutes. Looking at that crazy thing, wow, that got there. Let's hear 40 minutes, let's try it. So if we watched, or not watched, reading what I'm seeing there. If we have 40 minutes that have elapsed, how much water would we expect in the pool, right? Let's try it, see what happens. So we'll take our negative 38 over 5, multiply that by the 40 minutes that have passed, and add on that 716 that we would have started with. Looks like 412. Let's see. There's 400. Yeah, just a touch over. So yeah, we should expect about 412 gallons left in the pool, right? That seems to work. Let's try something else. What if we went to 100? All right, because we said it looks like our graph ends at about that point, so let's try it. What happens at the 100th minute? All right, here we go. We'll take negative 38 over 5, multiply that by 100, and add on, not subtract, add on our 716. Let's see what happens. Negative 44. Negative 44 gallons. So what does that mean? Well, it means that clearly we're going to end up at 0 before minute 100. Because notice at minute 100, it would say that we're 44 gallons in the hole, which doesn't make sense because a pool is a hole. But notice, in this case, our model tells us a number that doesn't make sense. So obviously our model is going to stop and break down at some point. And obviously minute 100 doesn't make sense. So we would have drained the pool before minute 100. That's one way we can interpret this answer. So this is what we're going to be doing today. We're going to be graphing our situations, drawing in that line, creating that equation, and interpreting what it means, and recognizing that sometimes, yep, our number will make sense. 412 in that situation, sure, seems to work. While in other situations, yeah, we might be able to plug a number in, but what we get out doesn't make sense, and we're just going to have to be cognizant of that. If you have questions or concerns, bring them with you to class. Otherwise, have a good day.